For the screencast of chapter 22, I have worked on two problems. On the first problem, you can see a box with 20 centimeter long, 4 centimeter height, and 3 centimeter deep. And you can see all over the box there is the presence of magnetic electric field. Here you can see E1 is coming from the bottom, E3 is on the top, and E2 is on the side. So it asks us like what you can conclude about the contents of box, and it says to input the numerical values. uh, we know that the electric flux associated with the closed surface of area A can be given by phi equals E dot NA. This can be written as EA cos theta, where E is the strength of electric field in which the surface is placed. Theta is the angle between the electric field and the area vector, and n is the just unit normal vector. So for the A, which is the area, we can get it by LW, where that is length times its width, and the electric field due to the top and bottom comes out to be phi equals ELW cos, this one in theta comes to be 0 because they are parallel, which comes out to be ELW. And so on the remaining face, the electric field and the area vector are perpendicular to each other. Thus the electric field due to the remaining faces is 0 because the cos theta is cos 90, which is 0. So now just changing the units to standard SI, that is the 3 centimeter to 3 to 10 to the minus 2 meter, the length to be 20 into 10 to the minus 2 meter, and the electric field through the bottom face is negative 1500 volt per meter, and the electric field through the top E plus is 600 volt per meter. So then the electric field flux from the bottom comes out to be E LH, and just putting the value from above here, it comes to be negative 9.0 volt per meter. And for the electric flux on the top, phi comes out to be 3.6 volt per meter, And according to the Gauss laws, the total electric flux is 1 by E naught times, and the charge enclosed by the surface, so phi is 1 by E naught Q. So the Q enclosed comes out to be phi E naught, and we already got the phi from above, which is negative 5.4 voltmeter, and E naught comes out to be 8.85 into 10 to the power minus 12. Here I forgot to put the negative sign. So the Q enclosed is negative 478 picocoulomb. So the total charge enclosed by the box is negative 47.8 picocoulomb. The next problem, here you can see there is a box, similar box, which is width is 14 centimeter, length is 0.2 meter, and you can see the magnetic field to be applied, which is horizontal. The B3 is on the top, B1 is on the bottom, and B2 is on the side. And it says to find the electric current in the area that is surrounded by the rectangular path. So the Ampere's law for a closed path can be given by the integration of B dot dl, which comes out to be mu naught I inside, where B is the magnetic field associated with the path, delta dl is the line element within the closed path, and I inside is the current passing within the closed path. So just a note to consider is that the magnetic flux due to the side of constant element is 0 because the line elements are perpendicular to each other, and as line element and the magnetic field are parallel to each other at upper part and the lower part, the magnetic flux through those lines takes a finite value. So just now applying the Ampere's law in counterwise direction for the upper part of element, we get B3dl to be B3L, and just putting the value, the theta is 180, and just putting the value, it comes out to be negative 1.2 into 10 to the power minus 5 Tesla meter. And similarly doing the same thing for the B2, it comes out to be 3.6 into 10 to the power minus 3 Tesla meter. So just getting the net magnetic is just adding the both, so it comes out to be 1.8 into 10 to the power minus 5 Tesla meter. So we know that the radiated is I inside mu naught, so we can get the current inside the area to be this much divided by this much, which comes out to be 14.3 ampere. These two problems are really cool experiment from which you can get the magnetic field and the charge inside the closed surface, closed area.